Hello everyone, welcome to NOVOSENSE's technical session on isolation technology. With the rapid growth of high-voltage electric vehicles, industrial systems, and high-efficiency power supplies for AI servers, isolation devices have become critical safety components that determine system safety and reliability. Today, under the theme of Basic Introduction of Isolation, I will walk you through the fundamental concepts of electrical isolation, explain the essential value of isolation devices in high-voltage systems, and share NOVOSENSE's technology roadmap and product practices in the isolation field. Today's presentation consists of 6 sections. First, we will introduce the definition of electrical isolation and explain why modern electronic systems increasingly require isolation. Second, we will compare the major isolation technologies used today, including capacitive isolation, optocouplers, and magnetic isolation. Third, we will explain different isolation levels, including functional isolation, basic isolation, dual isolation, and reinforced isolation. Fourth, we will introduce the international standards and certification systems related to isolation devices. Fifth, from a system design perspective, we will discuss the key parameters engineers should focus on when selecting digital isolators. Finally, we will share NOVOSENSE's development journey in the isolation market and introduce our Isolation Plus strategy. Let us begin with the definition of electrical isolation. In conventional low-voltage systems, electrical signals can be transferred directly between systems, allowing them to operate safely and normally. However, in many practical applications, interaction is required between high-voltage power domains and low-voltage control domains. Examples include EV traction inverters and battery management systems, industrial servo drives and motor drives, renewable energy and energy storage systems, high-voltage server power supplies. In these applications, direct electrical connection between high and low-voltage systems may allow common mode noise, surge voltages, or even fault currents from the high-voltage side to couple into the low-voltage control side. This can lead not only to system malfunction, but also to functional safety risks and, in severe cases, hazards to human safety. This is why isolators are required. The core functions of an isolator can be summarized in 2 aspects. First, it blocks hazardous high-voltage energy and destructive electrical signals. Second, it enables the safe transmission of control and communication signals. In simple terms, an isolator creates a secure information channel between 2 different voltage domains. This has become a fundamental building block of modern high-voltage electronic systems. With the rapid development of electric vehicles, energy storage systems, and industrial automation, the power electronics industry is entering an era of higher voltage, higher switching frequency, and higher power density. In particular, as third-generation semiconductors such as silicon carbide and GaN become widely adopted, switching speeds continue to increase, and DV/DT levels are rising significantly. As a result, common mode noise becomes more severe. High-frequency transient disturbances increase. EMC challenges become more complex. At the same time, customers continue to demand higher reliability, better functional safety, and longer service life. Under these conditions, traditional isolation solutions are becoming increasingly insufficient for next-generation high-voltage systems. As a result, isolation technology itself is evolving from traditional optocouplers toward digital isolation technologies. On this page, we compare the 3 mainstream isolation technologies currently used in the industry: capacitive isolation, optocoupler isolation, magnetic isolation. Let us begin with traditional optocouplers. Optocoupler technology has been used for many years and is widely deployed in industrial control, power supplies, and conventional communication systems. Its advantages include mature technology, high surge withstand capability, relatively easy implementation of dual-side ESD protection. However, with the emergence of new energy applications and high-frequency, high-voltage systems, optocouplers have gradually revealed several limitations. For example, relatively low common mode transient immunity, or CMTI, CTR, aging and drift over time, limited temperature performance, higher power consumption, greater difficulty in controlling input threshold consistency protest. As a result, the industry is increasingly transitioning toward digital isolation technologies. Digital isolation mainly includes capacitive isolation, magnetic isolation. Taking capacitive isolation as an example, NOVOSENSE adopts silicon dioxide as the isolation dielectric. Silicon dioxide offers extremely high dielectric strength, along with excellent resistance to high temperature and high humidity. In addition, capacitive isolators typically use differential transmission architectures, enabling outstanding CMTI performance. Today, NOVOSENSE third-generation digital isolators can achieve CMTI levels exceeding ± 200 kV per microsecond. This is a critical performance metric for applications such as silicon carbide, traction inverters, OBCs, DC converters, and energy storage systems. Magnetic isolation, on the other hand, is based on microtransformer structures and likewise provides excellent noise immunity and high-speed communication capability. Overall, compared with traditional optocouplers, digital isolation solutions typically offer higher CMTI, better input threshold consistency, wider operating temperature range rooms, higher CTI rating, better system-level cost performance. For this reason, virtually all high-voltage systems requiring electrical isolation are moving from the era of optocouplers into the era of digital isolation. After understanding the different isolation technologies, let us look at isolation levels. When selecting an isolation device, many engineers focus primarily on isolation voltage ratings. However, the true determinant of system safety is not merely the withstand voltage value, but the overall insulation capability and long-term reliability. Therefore, the industry classifies isolation devices into 4 isolation levels. The first is functional isolation. Functional isolation provides the isolation necessary for normal operation of the device, but it does not provide protection against electric shock. The second is basic isolation. Basic isolation provides a single layer of insulation protection. Under normal operating conditions, it protects the system. However, if the insulation layer fails, there is a risk of electric shock. The third is dual isolation. Dual isolation adds an independent insulation layer on top of basic isolation. Even if one insulation layer fails, the other can still maintain safety protection. The fourth is reinforced isolation. Although reinforced isolation uses only a single insulation structure, its safety performance is equivalent to dual isolation. In other words, it achieves the same level of protection as dual isolation within a more compact structure. Today, reinforced isolation has become an increasingly common requirement in electric vehicles, industrial high-voltage systems, energy storage systems, and server power supplies. It is also important to note that isolation devices differ fundamentally from ordinary analog or digital ICs. Isolation devices are, by nature, safety-critical components. They not only transmit signals but also directly affect personal safety and the isolation integrity between high and low-voltage systems. Therefore, isolation levels are not definitions that manufacturers can assign themselves. Capabilities such as basic isolation and reinforced isolation must be independently verified and certified by accredited third-party laboratories. Next, let us review the standards and certification systems related to isolation devices. In the field of isolation, international safety standards are primarily developed by the International Electrotechnical Commission, or IEC. Regional testing and certification are then carried out by organizations such as UL, VDE, CSA, TÜV, and China's CQC. For isolation devices, certification is not only a market access requirement, but also a critical guarantee of long-term reliability. Typically, the first page of an isolator datasheet lists all certifications obtained for different regions. For digital isolators, the key reinforced isolation standard was originally established by VDE and later adopted by IEC as a globally recognized standard. NOVOSENSE is the first semiconductor company in China to obtain VDE reinforced isolation certification and remains a leading player in China's digital isolator market. On this page, we further introduce several key tests and requirements defined in IEC 60747-17. For the maximum surge voltage test, both basic isolation and reinforced isolation devices must withstand 50 bipolar surge impacts. The measured voltage must not exceed 1.3 times the maximum surge voltage specified in the datasheet. In addition, reinforced isolation devices must pass a minimum 10 kV surge voltage test. When defects exist within an insulation structure, partial discharge may occur. Partial discharge refers to localized electrical discharge that only partially bridges the insulation between conductors. Although it does not immediately reduce insulation strength, repeated exposure to high voltage can eventually cause insulation breakdown. Therefore, non-destructive testing is used to detect such defects. For basic isolation, the partial discharge test voltage is 1.5 times VIORM, while reinforced isolation requires 1.875 times VIORM. Based on insulation lifetime data collected under different temperatures and operating voltages, Weibull distribution analysis is used to model the relationship between operating voltage, target lifetime, and failure rate. Combined with VDE-defined coefficients, VIOWM and VIORM can be derived. As shown, reinforced isolation provides longer operating lifetime and significantly lower failure rates throughout its service life. Once these tests have been successfully completed, the device is considered to meet the requirements for VDE certification. How should engineers select an isolation device? From a system design perspective, let us use digital isolators as an example and review 7 key selection parameters. The first parameter is isolation voltage. Since isolation products are safety-critical components, selection should always begin with safety requirements, with isolation voltage being one of the most important considerations. NOVOSENSE offers both basic isolation and reinforced isolation products, covering different voltage classes to meet diverse system requirements. However, engineers should not focus solely on test voltage ratings. Long-term reliability must also be considered. The second key parameter is ESD performance. Isolators are typically located at system interface boundaries and are therefore exposed to surge and electrostatic discharge events. Insufficient ESD capability may create latent defects even if immediate failure does not occur. NOVOSENSE devices achieve 8 kV HBM ESD protection, which represents the highest level of chip-level HBM performance. The third and one of the most important parameters today is CMTI. CMTI measures a device's immunity to transient disturbances and reflects its robustness in real-world applications. As silicon carbide and GaN devices become more prevalent, system DV/DT levels continue to increase, resulting in higher common-mode coupling currents caused by parasitic capacitance. CMTI describes the ability of an isolator to maintain correct output states during rapid voltage transitions. If CMTI is insufficient, transient disturbances may cause output errors or even short-circuit events, potentially compromising system safety. NOVOSENSE isolators provide CMTI performance of up to ± 200 kV per microsecond, ensuring reliable system operation. The fourth consideration is package and creepage distance. Package selection is not simply about footprint size. It is closely related to insulation capability and safety clearance requirements. NOVOSENSE offers SOP, SOW, and SOWW package options to satisfy different safety requirements. Package dimensions directly influence insulation performance. Although miniaturization offers many advantages, higher isolation voltage requirements generally demand wider packages. For this reason, NOVOSENSE provides standard body, wide body, and extra wide body packages. The extra wide body package offers up to 15 mm creepage distance and 8 kVRMs isolation voltage. A reinforced isolator in a single extra wide body package can provide insulation performance equivalent to 2 basic isolators connected in series. This is especially valuable in applications such as photovoltaic inverters. The fifth parameter is data rate and propagation delay. In gate driver applications, even nanosecond level delay mismatches may affect switching synchronization. The sixth parameter is power consumption. Because digital isolators are based on CMOS architectures, they generally consume significantly less power than traditional optocouplers. Although power consumption influences thermal design, it is usually not the primary selection criterion. Finally, operating temperature must be considered. Temperature affects threshold drift, dielectric characteristics, and long-term aging. For automotive grade 0 applications, devices must support operation from 40 degrees Celsius to plus 150 degrees Celsius, placing stringent requirements on materials and process technologies. After more than 10 years of dedicated development in the isolation market, NOVOSENSE has become a globally leading isolation chip provider. NOVOSENSE began digital isolator R&D in 2016. In 2017, we launched our first-generation digital isolators and subsequently expanded our portfolio to include isolated interfaces, isolated sampling, isolated power supplies, and isolated gate drivers. In 2021, we achieved mass production of a full range of automotive-qualified isolation products. By 2025, cumulative shipments of NOVOSENSE isolation chips had exceeded 2.7 billion units. From 2020 to 2025, isolation chip shipments achieved a compound annual growth rate of 92%. Today, NOVOSENSE maintains the leading market share in China's isolation chip market. Building on years of technological accumulation and continuous product innovation, NOVOSENSE has introduced its Isolation Plus strategy. Our goal is to lead the isolation industry through core technology IP and a comprehensive product ecosystem. The Plus carries three meanings. First, it represents enhanced safety. Through our core technology IP, including isolation platforms exceeding 10 kV withstand voltage, ultra-high CMTI technology, and functional safety design, we help customers establish higher levels of system safety. Second, it represents a full product ecosystem. We provide much more than standalone digital isolators. Our portfolio includes digital isolators, isolated interfaces, isolated sampling, isolated power supplies, and isolated gate drivers, enabling one-stop isolation solutions. Third, it represents deep application empowerment. For high-voltage applications such as EV platforms, high-power PV, energy storage and EV charging systems, and AI server power supplies, NOVOSENSE provides not only Isolation Plus devices, but also system-level solution capabilities. Looking ahead, competition in the isolation industry will no longer be defined solely by individual device performance. Instead, success will increasingly depend on platform capabilities, system expertise, and ecosystem strength. Through the Isolation Plus strategy, NOVOSENSE aims to deliver unique value and help customers build safer, more reliable, and more efficient systems. That concludes today's presentation. Thank you for your attention. As electric vehicles, energy storage systems, and AI power infrastructures continue to evolve, the importance of isolation technology will only continue to grow. NOVOSENSE will remain committed to advancing core isolation technologies and driving the development of high-performance isolation chips, providing the industry with safer, more reliable, and more efficient system solutions. Thank you very much.